Hello there, math fans. Dr. Andy Lovelace here. I'm going to give you a proof of the second derivative test and also give you a feel for what it's about. You can look up online and you can see a formal proof where they prove some lemmas about quadratics, but I'm going to just kind of step into it directly, and then we'll have a few details we'll have to fill in as we go to give you a taste of really what it's about. For my students in my Calculus 3 course, we don't have to know the proof, but I think it's kind of nice to see something. So watch my previous video for the actual calculation. I have an example there in the corner of the screen, and you can see that visual. Ultimately, I've talked about how we're trying to get a handle on the concavity. For example, at that saddle point there, which is 0, 0, you can see the concavity changes. It's concave up in some directions, it's concave down in other directions around the point, and that's why we call it a saddle point. Okay, so we're really trying to figure out when is the concavity the same in all directions and when is it different. If you want me to state it here, first we find the critical point. So critical point is a point where both the partial derivatives are equal to 0. Sometimes we include when one or the other partial derivatives don't exist at a point in the domain, but for now let's just talk about a place where both partial derivatives are 0. And then we ask you to compute this unusual thing. We say compute all these second partials at the given point, and you go one by one through the points, and you compute this number, you compute this number, you compute this mixed partial, and you square. And ultimately what this weird theorem says is that if this thing, whatever you get when you plug in your critical point, is negative, then it's a saddle point. And ultimately that means the concavity changes in some direction. That's really what that means, such as in the picture. If d is greater than 0, the concavity does not change. So the moment you have this, then you know it's either a local max or a local min. So this means concavity the same in all directions. So I think I ran into my picture. Let's get rid of that picture. That means you need to then go look. So what I mean by go look is you look at your partial derivatives. If the partial with respect to x twice is positive, then all of them have to be positive. So actually you could either check this or this, because this will automatically mean that this is positive. Sometimes I like to write both, even though I don't need to. Then that means it's concave up in all directions, and that means it's a local min. And in your head, you should be thinking a smile, concave up in all directions. And if f of x is negative, that means f of y will also be negative. Then it has to be a local max. And you should be thinking concave down in all directions. So that's it. That's that thing. It says if d is equal to 0, it's inconclusive because there are examples where d is 0 and it's any one of those. What I want to do here is talk about some elements of the proof and give you sort of my casual proof for it. There's a piece of it that's a little more involved, but I'm not going to start there. I'm going to start with doing this directly. So using what I've been talking about, we're trying to figure out how we can confirm that the concavity is the same in all directions or it changes. Unfortunately, that requires understanding of the directional derivative because we've only done the partial with respect to x and y, and so we only know the slopes in those directions. The mixed partial does give us just enough information, but we don't really give you a clear handle on that. So here's how this goes. If you haven't watched my previous video about directional derivatives, I talk a little bit about this, but I'm going to give a little bit of a background. So imagine looking down from above. I'm standing on one of these points, and I'm looking down on it. So here I have this point. Let me move this so you can actually see it. And I'm looking down from above. So imagine you're standing on the contour map, and you're at this point AB. And you look in some direction other than, so the two directions we've looked are this direction, the positive y direction, and the positive x direction. But you really can look in any direction. And we are trying to do that for this discussion. So imagine I give you an angle, and I tell you to look this direction. Well, one way to say that is I want to look in this direction. That's a unit vector looking in a certain direction. I've talked about that in previous videos. That's the directional derivative. So if I step slightly in that direction, it actually gives this one variable function, and we can study it. We can actually study the concavity. We can take the second derivative of that, basically. That's the story. And that's exactly what we do. And a bunch of things pop up. So if you missed my previous video on directional derivatives, again, that's not part of this course, but if you want to understand why this is true, then you do have to look at this a little bit. So briefly, I'm going to try to make it so I can see what I'm doing. Let's take the statement. Let's make it much smaller. And let's start talking through this. So in the previous video, I talk about how you can actually take the derivative, use the chain rule, and that sine and cosine pop out. So if you missed that, go back and check that out. But that's the directional derivative. You get this cosine, you get this sine. And then take the limit as h goes. So that's the first directional derivative. Unfortunately, we do use a d for that, which is different than this d. Oh, darn. Okay, so what we're going to do is take the derivative again. We're basically going to take the second derivative. And the way you take these directional derivatives is you take the derivative with respect to x, then multiply it times cosine, take the derivative with respect to y, and multiply it times sine. That's the takeaway from that. Okay, so now let's jump into the second. So we're going to do the second directional derivative, which is saying this. And that's really it. The proof is about playing around with this. And I was looking through our text, and I always thought they had a proof in there, and I realized they only proved a special case. So I was a little sad. So I was like, I'll just mimic their proof. And then today I realized, oh, they don't do the full proof. And so I got to think today, which was fun. I got to figure it out myself. So let's talk about what happens. So now we're going to play around with this. So we're going to take we're going to take the derivative of this first with respect to x. So this is the first derivative. We're going to take the derivative of the first derivative with respect to x, multiply it times cosine of theta. This is this chain rule. We don't do all these pieces, but I just want to show you this where it comes from. So what happens if you take the derivative with respect to x is you get f of x. And then we can distribute the cosine. So you get this little cosine squared of theta. And then you get f of yx. The order actually doesn't matter because of Clairaut's theorem, assuming we have continuous partials. But we're going to assume that. And then we have this cosine of theta, sine of theta. This is what I did earlier today. I was just thinking about this, and then this twice. Sine squared of theta. And that's really it. Basically, you could say this is our second derivative test, is we run through all the angles. I know I made it too. We run through all the angles. We figure out, is this always positive or negative? So we're trying to see, is this negative always? Or does it change? Is this positive always? What can we say? Is it concave up in all directions? In all directions for all theta? So that seems kind of challenging. So if it's positive for all theta, then it's concave up in all directions. If it's negative for all theta, then it's concave down in all directions. And if it changes, it's a saddle point. So that's really what we're trying to do, is just figure out if this thing is positive or negative. So there's various proofs you can do based off of that, but there's several things you can clean up. So let's do a little bit of cleanup. You can see these are the same. So let's write f of xx, cosine squared of theta. And again, this is what I did earlier today, and I was like, oh, okay, the proof is not in our book. So what can I say? And I'm no expert in this area. Like I said, if you want a more polished proof, I'm just going to talk through how we think about this. So ultimately, I started to think, what could I do to this? And this is the challenge. But I realized that maybe part of the challenge was that I had sines and cosines. So the idea I had was, what if I pull out a cosine squared? Just to make our lives a little easier. And it actually makes things quite a bit easier, as I'll show you here. So I'm dividing everything by cosine squared because I'm just trying to see if I can simplify this a little bit. Now, if you think about what happens when you divide by cosine squared here, one of the cosines cancel, and you end up with a sine over cosine, which is actually tangent. So that's kind of nice. When you divide this by cosine squared, you get sine squared over cosine squared, so you actually get tangent squared. That's kind of nice. So ultimately, here was my thought. Okay, this is positive. It's greater than or equal to 0. Only equal to 0 at certain angles. So now I just need to figure out, is this positive or negative, or can this change? That's what we're trying to figure out. If it can possibly change, we call it a saddle point. If it's always positive, we'll call it a local min. If it's always negative, we'll call it a local max. That's what we're trying to do. Okay. So here's the thing that I sort of observed today, and I'd seen this before. This is not my invention, but I had to get to this point to realize it. Is we're trying to play around with this based off of the other values. What can we say? If you look carefully at it, it's actually a parabola. What do I mean by that? If you let t equals tangent of theta, just for a moment, and just focus on that, then you get something that sort of looks like this. Let's use a different color. You get a t squared. I don't know what to call it. Let's call it w or something. Let me make it so you can actually see this. Sorry that I'm not very good at managing this, but I'm trying to, as I said, my goal here is just to talk through this, not give you something totally polished that hides what we're actually doing. Okay, so I'm going to think about this quadratic function. And this actually happens a lot in quite a few of your math classes. You'll see it again in Math 207. There are many situations that are really quadratic applications in disguise. So if you don't see it, here's what I'm saying. I'm saying this is my A. So right here I have f of y. This is my B, f of xy at that particular point. So again, we're just talking about at 1 year critical points. And this is f of xx. And the t is tangent of theta. Now, a nice thing about tangent is tangent actually takes on all the values. So t could be anything from negative infinity to infinity. If you graph tangent, it goes up. I'll mention maybe briefly at the end why that matters. Okay, if you're analyzing a parabola and you want to know, is it always positive? Is it always negative? Or does it change? Think about a parabola that's always positive. This is what I was thinking earlier today. I was like, well, if the parabola is always positive, it's like this. And actually, we'd include something that just touches, would also, because it wouldn't have changed concavity. So anything that looks like this. Now, in order for it to look like that, think about what has to be true about the parabola. It can't cross. So there's two things that have to be true. A, and this ties in. A has to be positive for it to be a smile. And two, it can't have any solutions when it's equal to 0. Now, if you set this thing equal to 0 and solve, what do you get? You get to same the quadratic formula. Now, unfortunately, it's 2b. Negative b plus or minus square root b squared minus 4ac all over 2a. And it boils down to this. As I said, this comes up a lot. this, in order for you to have no solutions, no places it crosses, that right there needs to be negative. So the other thing we need is that 4b squared minus 4ac has to be negative. Now you can divide everything by 4, so we don't really need the 4 there. That's it. This would guarantee that this is always positive, which would mean you would have a local min, because it would be concave up in all directions. I know that was a bit to follow, but I really wanted to break this down. I've only seen it written in sort of complicated ways. That's it. Now, what are the pieces there? Well, this b squared minus 4ac being negative is the following. So let's write down what that would be. We have the mixed partial squared minus the partial with respect to y twice, the partial to xy needs to be negative. At some point somebody thought, oh, I would rather the negative case be the saddle point, and so they wrote it in the opposite order. F of y, and then everyone copied after that. So if this is positive, then that means this is negative. And if f of yy or f of xx is also positive, then it's concave up in all directions. So that's a nice little chase. And now you can see where the other cases come from. It's all this quadratic. Okay, let me know if that's interesting to you, but let's do the other cases. So the other cases are this. So we'll keep that quadratic in mind. What else can happen with a quadratic? Well, when is a quadratic always negative? That would be the same condition. And let me scroll up a little bit because we've just broken it down to this. So it's the same condition that you need to have f of xx, f of yy minus f of xy squared positive, because that guarantees you have no places it crosses. And then you need a to be negative. Now a is f of yy. Now you might say, I thought it was supposed to be, and that means it's a local max on our function because it's concave down in all directions. So again, this right here, we're trying to guarantee that this is always negative or always positive. I sometimes see this in class. You know, if I tell you that this is a positive number and this is a negative number, it forces this to be a negative number. You can't have two numbers multiplied together, one of them be negative and the product be positive without the other one being negative. Okay. Lastly, and this is the interesting case and why you have to argue it this way. The book argues what I just did in a different way, but that argument doesn't work for this other case. Okay, one last case. How do you know if it switches? So let's erase this. So the three things that can happen with your parabola is it's either going to be always below or always above, possibly touching, or it's going to cross. How can you know if it crosses? Lots of ways it can cross. But if it crosses, it's going to have these two solutions. Now back to our quadratic formula. How do you have two solutions? You need the thing under the radical to be positive. So the same argument with the flip sign. So instead of having f of xx, f of yy minus f of xy squared greater than 0, you need f of xx, f of yy minus f of xy squared less than 0. If that's happening, then that means this function will be both positive and negative. That means this will be both positive and negative. So it's an interesting little bit of logic. It's kind of cool to see that it's basically the discriminant again. And as I said, you'll see it again in Math 207. These little arguments based off of these small things. Less than 0. Okay. Again, that wasn't super polished, but it's kind of fun to see that as messy as that function was, it was possible to say something without actually digging into theta about when it will always be positive and when it will always be negative. Okay, hope you found that interesting.